Welcome to Lecture 28. And Lecture 28 is going to discuss POGIL Activity 12, which is the electrophilic addition to alkynes. And I need you to get out reaction sheets, and I think we're going to cover around 9 reactions. So you all can keep track of that. You'll need 9 reaction sheets. All right, so the first one, Model 1, which is page 150, is titled Electrophilic Addition of HX to an Alkyne. And so, do we have a terminal alkyne or an internal? Okay, this is called a vinyl bromide. Okay, that's a vinyl bromide. And then we add a second addition of HBr, step 2, and what do we get is our functional group. So if you're filling out your reaction sheet, your starting material would be an alkyne, your reagent would be HBr, and you would get a geminal dibromide. Now, this with the hydrogen at the end, it's called a terminal alkyne. And you know, terminal alkynes, they're acidic, so we can deprotonate that using sodium amide and make the acetylide ion. Okay, so question number 1A. What product is formed after the addition of one equivalent of HBr? So if you add one equivalent HBr, it's going to add across this carbon-carbon triple bond, and we get hydrogen added there, and we get Br added there. That's called a vinyl bromide because the Br is bonded to an sp2 carbon. In the product formed after step 1, the Br is bonded to one of the carbons of the double bond. True or false? I said true. Based on your answer to 1B, complete the following sentence. The name vinyl bromide means that the bromine is bonded to an sp2 carbon. Okay, so vinyl bromide means this bromide, the bromine is bonded to the sp2 carbon, has a double bonded carbon. Okay, 1D. What product is formed after the addition of a second equivalent? So now we added a second HBr to this other pi bond, and you see that you have the Br here, and then the next HBr adds there. And that's called a geminal dibromide. In the product formed after step 2, the two bromine groups are attached to, did you circle same carbon? Based on your answer to 1E, the term geminal means the bromine groups are bonded to the same. Okay, that means in German or Latin, I think Latin means twins. So it's like they're bonded to the same carbon. The other one we saw was vicinal, and that was the neighbor. Okay, let's answer 2A. How many pi bonds does alkyne have? Did you say 2? 2 pi bonds to the same carbon. Okay, wait a minute. Okay, 2b. An example in Model 1, how many pi bonds are reacted in step 1? Just one. How many pi bonds are reacted in step 2? 1. How many pi bonds have reacted in total? 2. Is alkyne acting as a nucleophile or electrophile? Okay, that's always going to be a nucleophile because it's a pi bond. The pi electrons form the first bond with H plus HBr, and then the Br minus attacks the vinyl bromide. So compare the reaction. In your groups, discuss what is similar to these reactions to the alkene. Okay, so basically this pi bond is going to bond. HBr is acidic. I think this is the next question as well. So we'll just go ahead and show you what the concept is leading up to. So when you draw this with HBr, those pi electrons go here, those electrons go there. Now we have okay, so you got to decide where the hydrogen is going to go, because it's got to go across this bond here. And you see here that the hydrogen went here. Okay, so this hydrogen goes here to generate a vinyl carbocation. So the alkyne first acts as a nucleophile. This is your electrophile in both alkyne and alkene. The H plus adds to the least, so H plus adds to the least substituted carbon. Whose rule was this? This is kind of like Markovnikov, because we want the most stable carbocation. And this is actually called a vinyl cation. Okay, so that's a vinyl cation. Okay, looking at the questions for 3. Consider the addition of HBr to the alkyne as shown in Model 1. Draw 2 possible vinyl cations using curved arrows to show the formation after the addition of HBr. Okay, so there's one. If you did the other, you would get so if you had the hydrogen here, but and of course the Br would be kind of hanging out in solution. This would be the least substituted carbocation. Okay, of the 2 vinyl cations drawn above, which would be the most favorable? Did you pick the top one? Explain why. Vinyl cation 1, because the methyl groups, it's the hyperconjugation, right, would stabilize the carbocation. Check that the most favorable vinyl cation from 3b leads to the vinyl bromide showed in Model 1. So then you want to draw the next reaction, which would be so there's step 1. And now we have the bromide here, and it's going to act as a nucleophile towards the carbocation. and then you get bromide there. And look at your model 1. Is that in fact the vinyl bromide that you got? Yes. So you just draw that reaction mechanism there. Does this follow Markovnikov's rule? Did you circle yes? Starting with the vinyl bromide drawn here, using curved arrows, the two possible cations formed after the addition of H plus in the second step. So if you take this here, we'll just go from here, and now we're going to add another HBr. So we still have this nucleophile, and you have the acid HBr, and here we have our first Br, CH3, and now we have to put an H plus on one of these carbons. And so if you put the H plus here, that's going to give that carbocation. If you do HBr here with the H here, then you're going to get this carbocation. And so they want you to show all of those. I think I drew this wrong. Should that be an H? Yep, H, 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 a hydrogen. All right, so there's your two that they wanted to see in problem 3D. Given the structure of the geminal dibromide, so the geminal dibromide, which one? So then the Br here adds here, right? So the geminal this is your geminal dibromide. Has to follow this carbocation. What two cations from answer 3D must be more favorable? So we just circled that one. And then also it shows resonance. So if you had to do resonance for this, these electrons would go here. Bromine can have an expanded octet. So I'm going to draw my resonance arrows here. And it can withhold a positive charge. So this is actually very favorable. So this is very stabilizing here. So this has two resonance structures. All right, now for 4. Question number 4. In the addition of HBr to 2-pentyne, so draw 2-pentyne, 1, 2, 3, 4, 5. Okay, so that's 2-pentyne. You're at an HBr. Draw the two possible cations that can form after the addition of H plus in the first step. All right, so this is your nucleophile. And you're going to add the proton. That's going to generate the bromide anion, and you're going to get, you can get, so H can go here, and that gives the other one a carbocation, or you can get the hydrogen going to the other carbon. Now, let's look at the substitution here. This carbocation is substituted with this group. This one's substituted with this group. Okay, so those are the two possible carbocations you can get. The vinyl, these are called vinyl cations. Would you expect any difference in stability? So what's 4B? No, they're equally substituted. Okay, so notice that the difference here, this is an internal alkyne. Draw the two geminal dibromides expected of the reaction of 2-pine with excess HBr. So you're going to get both Br, Br, CH2, CH3, and you're also going to get this compound. So you're going to get a mixture of both of these compounds in equal amounts. All right, number 5. Next, consider the addition of halogens to alkynes. So this is a second reaction that you need to get a reaction sheet. Remember I told you there's about 3 reactions per model. So we've just gone over with one. So you just saw the a reaction sheet with one equivalent of HBr, and then you could have 2 equivalents of HBr or excess HBr, and you get the geminal dibromide product. Okay, so that's one reaction. This number 5 is the second reaction. Okay, so get out a new reaction sheet, and this is when you do halogens like Br2 to alkynes. So you got an alkyne, this is your reagent, and then what's 2-pentyne? 1, 2, 3, 4, 5. See how I make that linear? 1, 2, 3, 4, 5. Okay, and you're reacting it with Br. And the first thing you want to do is one equivalent. So here, you do this. Now, if you remember, with an alkene, it made this bromonium cation. Okay, so 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So you're going to get this intermediate, and then, so you can imagine this would come in. Remember, it polarizes this, and so now we have the Br minus. It's going to hang out with the plus, and then it's going to come in and open it, and then you're going to get a double bond, but you'll get Br. You get Br. They're anti. Okay, so this is anti-addition. And then that's one equivalent. And then what if you add 2 equivalents? So if you look at 5B and you add 2 equivalents of Br, then you would have another you can imagine that this would attack here. This is delta positive, delta minus, and then you would get this bromonium ion, and then this Br minus would come in, and you would open it up. And so on your sheet, on your reaction sheet, you would write what kind of product. What would you call this product? With excess, with two equivalents, you would get tetrabromide. And this would be a dibromide, vinyl. And this would be vicinal because they're on neighboring. This is a vicinal product, and this would be the tetrabromide. Now I said you would have three reactions, so another reaction I need you to do is what if you add peroxides? So your book does one equivalent of HBr. So HBr, and what if you add peroxides? And your roar, that's what I was telling my students, what if this was like just an alkoxy peroxide or something like that? Okay, so let's do the pentyne again, 2-pentyne. Okay, no, that's not would be, that wouldn't be a good one to do. We've got to do a terminal. Okay, so we're just going to do this. All right, HBr, and you can just do this, or like I said, you might see the R, the roar. Okay, you might see this. Okay, this does a different reaction mechanism, free radical mechanism. Okay, so if you're to do this mechanism, you got to show initiation. So you end up having light, by the way. So CH3, this is a weak oxygen-oxygen bond. It does homolytic cleavage. And you have two initiation steps because this has to generate a bromide radical. So now this goes here. And now you have an alcohol, which we don't care about, but you get a bromine radical. The bromine radical is what you're going to put in your propagation step 1. So here we have plus the bromine radical, and this is going to add, and you're going to get, it's going to add here, and this is going to make a bond. So you're going to get the radical there. It's a vinyl radical. You can put in carbons if you want. That makes things easier for you. Hydrogen here and the bromine there. Okay, and there you go. Now we have to react this free radical with propagation 2. It's going to react with another HBr. And so this one electron will add here, take away H, and you will get CH3. That will add a hydrogen there. You will have still a carbon-carbon double bond. And there you go. And so this gives you the anti-mark vinyl bromide. And the key is here, it's a free radical mechanism. So it's a totally different mechanism. It's free radical, not electrophilic addition. And that's why it's important to bring this up. So your book does one equivalent. So there you go. That's model 1. Now let's go on to model 2. So model 2, hydrogenation of alkynes. Okay, so hydrogenation is the addition of hydrogen. And hydrogen is hydrogen gas. You get a little gas. Okay, And that would be how you would do that. Notice this is linear. And there are two reactions here in this model. And so after we do this model, I will show you a third reaction that you're required to know for the assessments. This is not isolated. And we have seen this reaction. This is catalytic hydrogenation in the alkenes. This is equation 1. And then H2 Lindlar's catalyst. We're going to talk about what Lindlar's catalyst is. These are very important reactions. This is equation 2. All right, so question number 6. Consider the reaction shown in model 2. What functional group is formed in equation 1? So what is this functional group? An alkane. Okay, so it's an alkane. What is the functional group in equation 2? An alkene. Okay, so you should have two different reaction sheets with these two different reactions. So if you need to stop what you're doing right now and get those reaction sheets out. Okay, so one forms an alkane, A-N-E, which is a saturated carbon, and the other one's an alkene, which is unsaturated. 6C, describe what is different about the reagents that results in the formation of different products in equation 1 and 2. Well, what do they both have? They're both using hydrogen gas. Now, what is Lindlar's catalyst? Okay, Lindlar's catalyst is poisoned palladium. So you can see Lindlar's catalyst in your textbook, and it's basically palladium that has been poisoned with barium sulfate and quinoline. Okay, so this is called quinoline. And so when you poison the palladium with barium sulfate and quinoline, do you remember how I told you that this is like a metal? So you got the palladium metal, and then hydrogen gets in situ, it's called intersituated, I think that's the word, where it gets into the palladium pores. And remember we had the alkene come, and the alkene comes over the palladium metal, and then hydrogen delivers to this side of the molecule to give us a syn addition. And that's why you have the syn here. Okay, now you can't stop that when you have an alkyne. It's the pi bonds are attracted to this metal. Okay, now if you poison this with barium sulfate, so you poison the metal with barium sulfate and quinoline, then it will actually only deliver one set of hydrogens, okay, because they're poisoned now, and it will actually stop and deliver just 1 mole of hydrogen. Okay, so you have to poison the palladium catalyst. So you still need hydrogen gas, and you still need palladium, but the difference is you poison you slow the reactivity of the deliverance of the hydrogen by using barium sulfate and quinoline. It still delivers hydrogen from the syn, so you see you're going to get a cis alkene. That's going to be important. Okay, explain why Lindlar's catalyst is referred to as a poison catalyst. So hopefully you can do that. If the hydrogenation of an alkyne using Lindlar's catalyst, okay, syn addition occurs. This is syn addition. The resulting alkene geometry would be, what did you circle? You circle cis. Does your answer in 7A agree with the geometry shown in equation 2? Did you say yes? Can the alkene in equation 2 be rotated so the opposite geometric isomer is formed? Can you rotate around a double bond? No. Okay, so you don't form the trans. If alkenes cannot freely rotate, discuss in your groups how the mechanism of hydrogenation would need to be different in general terms so that the opposite geometric isomer could be formed. Don't answer that. Instead of answering that, we're going to add our third reaction. So this is the one reaction. It's just called catalytic hydrogenation, and the alkyne will go to an alkane. This is your second reaction where you take an alkyne using Lindlar's catalyst and you make a cis alkene. And I'm going to show you another reaction in which you make a trans alkene. Okay, so this is our third reaction where you're going to make a trans alkene from an alkyne. So you need another reaction sheet. Okay, so we'll keep with our compound here. Okay, and now the reagents is sodium, solid, and liquid ammonia. And when you put your sodium in, which you have to be careful because it will catch fire, and you put it in your reaction flask, and then you have to condense liquid ammonia. You have to have pretty much, you have a balloon of hydrogen here. Okay, so you might have like a little green balloon. It's kind of fun. And you'll have hydrogen. No, you don't have hydrogen. What am I talking about? Okay, that's the other reaction. Okay, so you basically have your reaction here, and it's going to make a blue liquid. What does that blue liquid mean? Okay, because sodium is like silver, and ammonia is clear. But when you combine these two, you get this blue, bright blue liquid. It's so beautiful. It's my favorite. Okay, the blue is actually a free electron. That's what that means. It's a floating free electron. And this actually generates a free electron. And what happens here is the mechanism. It's a free radical, so the electron adds, and you have this mechanism in your book, okay, page 480 in your book, and so the electron will add to your, you see how I have a half arrow? And then these two electrons will go here. Okay, so you get this. One electron, and then you get a double bond, and then just make that carbon CH3. And then these two electrons here will actually go on the other side. Okay, because why? These electrons want to be far away from this one electron. Electrons repulse each other. Okay, and so when you get two electrons like that, then in your ammonia, anytime you get two electrons, it can now deprotonate. So these electrons now here can go and deprotonate. And so now you get, you still have this vinyl radical cation. And now we can put this hydrogen here. We have a CH3. Okay. And I guess I should put a negative charge there. All right, and then we have another, it picks up another electron. Whenever you have that. This is called a vinyl radical. And then, so the next electron will add here, your fishhook arrow here, and then you get hydrogen here, CH3 here, and now you have the anion here. And when you have that, then it will pick up another hydrogen from the ammonia. So your hydrogen source is from ammonia. And so now you have one hydrogen delivered on one side, and you have another hydrogen delivered on the other side. And you see how this is a trans alkene, and it's a free radical mechanism. Okay, so that's how you get the trans alkene. Now, that should take you through model 2, and we have one more model to go, and that's hydration of alkynes. So model 3, if you'll work through that. This is your last POGL model for organic 1. So we're going to add water to our alkyne, and our reagents are going to be mercury, they say acetate, but it's actually mercury sulfate and sulfuric acid is one of the reagents. Okay, so if you're doing this and you want to go ahead and put your reaction sheet, you're going to have one reaction sheet where this is your reagent, and then you're going to have another reaction sheet where this is your reagent. And you do a 1,2 with hydrogen peroxide and sodium hydroxide. So these are your two different reagents. What is the, this is isoamyl, diisoamyl boron. So isoamyl has 5 and it's iso group. So 1, 2, 3, 4, 5. You can buy this reagent. And what this is it's a sterically hindered boron reagent. And so it can deliver the boron with diisoamyl to one of the carbons, and then it can deliver the hydrogen to the other. You probably remember BH3 and THF for the alkenes, so it's very similar. And you probably remember mercury acetate and water for delivering of water to the alkenes. So the reagents change just a little bit, but we're still adding water. Okay, so the nice thing about this is we only have to cover 2 reactions. So we are down to 2 reactions. So I misspoke. I said you had 9 reactions, but you really only have 8 in this POGL. Okay, so we're down to the last 2, and let's see what the model does here. So let me redo this down here. Okay, CH3. We're going to add water, and this is called a vinyl alcohol. It's also called an enol. Right? And we have equilibrium arrows here, tautomerize, and you're going to see your product here is a ketone. Now, I tell my students, what does the fox say? You all remember that song? What's the fox say? Anybody ever know what the fox says? Well, what does the donkey say? It says enol. Enol. Okay? So let's answer question 8a. For the addition of water, H2O, to the alkyne, So you see how we've added water to the alkyne to give a vinyl alcohol. What is another name for vinyl alcohol? It's enol. And what's the En stand for? An alkene. There's your alkene. And what's the Ol stand for? Alcohol. There's your Ol. Okay, so that's where you get the enol. And it's those functional groups. The vinyl alcohol rapidly tautomerizes, and tautomerization is an equilibrium to form a ketone. Based on the arrows depicting this step, which compound would you expect to be the most stable? Did you say ketone? Describe what happens in general terms in the tautomerization step. So what's happening here is this hydrogen is over here. Okay, so still have this hydrogen here. So the hydrogen from the OH goes to the neighbor, you could say the vinyl carbon. So these electrons go there. I do this when I show my tautomerization, and I just want to say the books will show the mechanism for tautomerization, and if you ever have to draw the mechanism for tautomerization, it's considered an intermolecular mechanism, but I'm going to draw it as an intramolecular because I don't want to go through the 6 steps to make it an inter. But so when I do my tautomerization, okay, so we've got our, I just do this. I say, okay, these electrons are going to take this hydrogen away. No, that's not right. Right. These electrons from the pi bond are going to take this hydrogen away, and then those electrons go down to form the ketone. So, and I do would be an intramolecular, but studies show it is an intermolecular where you get protonation, deprotonation, protonation, deprotonation. But some places don't really make you even learn the mechanism. It is in your book, so I will tell you that that's the appropriate way, but you can see where this is so simple. So it's these electrons basically are coming and taking the hydrogen to form a new bond here. Those are those. And then these electrons here form the double bond, and that's a ketone. I also want to say something else. You've run into Linus Pauling with the Nobel Prize for the electronegativities. Linus Pauling actually discovered the DNA basis structures and proposed the structures before Watson and Crick. Okay, but he never got credit for it because he had the wrong tautomers of the nucleic bases, which I think is so sad because at pH 7, which our body is, you see that the carbonyl is formed. Okay, the carbonyl is more stable. He drew the bases with the alcohol. And what's amazing about this story, and I have to tell it, he was sick for a few days. He did most of his research his own. He was in University of California. I want to say Berkeley, I think. I'm not sure. But anyway, he was home and he was sick, and he had someone that helped him and took care of him and whatever. And he's like, he asked her to bring he woke up from sleeping all day, asked for a pencil, a ruler, and a piece of paper. And that's how he came up with the tautomers, the enol tautomers of the nucleic acids. Okay, so that is my tautomerization enol speech. Where are we at? D. In the hydration of propyne above, does the addition reaction occur according to Markovnikov's rule? Okay, so is the OH being added to the more substituted carbon? Yes. So you see that the OH here is added to the more substituted carbon. So that's Mark's rule, yes. Ketyl enol tautomerization. So number 9. Ketyl enol tautomerization is also called a proton jump, as the proton of the OH group jumps to the neighboring carbon. What bonds are being broken in the vinyl alcohol undergoing tautomerization? So let's draw this again. So we have the OH here. We have the hydrogen, hydrogen. Okay, so we've added a hydrogen and an OH. So we've added water across the triple bond. And it's asking what bonds are being broken in the vinyl alcohol undergoing tautomerization. So this bond is being broken. The C-pi bond is being broken. And then the OH bond is broken. And what bonds are being formed? You're forming a new carbon hydrogen bond. So when we draw the enol tautomerization product, we now have a new carbon hydrogen bond, and we have a new carbon double bond, carbonyl bond formed. Draw the keto forms for each of the following enols. So for 9C, draw the keto forms. And I like drawing my little electron flow arrows. So I will draw mine that way. You don't have to if you don't want to, but it might make your life a little easier when you see the enol. It's like a new functional group, so you want to be able to recognize it. And anytime you see an enol, you need to realize that it tautomerizes, because that's what enols do. All right, so here is an enol. So you have to recognize that you have an ene, the carbon-carbon double bond, and you have an OH, which is the ol. So here's our enol. And this, I always do this. I say these electrons go here. All right, so then those electrons here go there. So when you draw this, you're going to draw the ketone. And so this hydrogen went to this vinyl carbon here, and these went to there. Okay, so there's your ketone. To here, these electrons are going to go here, and then those electrons will form the ketone. So the nitrogen's going to get the hydrogen, and the carbon's going to get another bond there, so we can redraw that. Nitrogen is going to get the hydrogen, and then you're going to get the oxygen, CH3. Okay, we have another enol here. So this is your hydrogen. Those electrons are going to go here, and then those electrons will go there. So if you draw this, and there's that new bond, and then this got the hydrogen there. Okay, so number 10, below is the acid catalyzed hydration of 1-butyne. So number 10, H plus, and water. All right, so what happens here is you're going to get, well, I'll go ahead and, okay, the product shown above is, do you see that we have oxygen and we've had hydrogen. So the oxygen adds to the more substituted carbon. So you got two carbons to choose from. You got this carbon or this carbon. And the oxygen added to the more substituted, so that's Markovnikov's. Using your knowledge of the acid catalyzed hydration of alkene, devise a mechanism for the above reaction using curved arrows for the electron form flow. All right, so your mechanism you would want is the nucleophile here. These electrons would get protonated, and that would add the H here. And now you have an alkene, and you're going to get a carbocation on the next carbon. And now the water is your nucleophile, and that's going to come in here. And so you have this intermediate, and you can just go ahead and do the deprotonation, and you can see that what is this new functional group? This is an enol. And then what do enols do? They tautomerize. So then these electrons here will go there, and then you can go, and you can see how that gives you your product. And that is a ketone. So if I was doing my reaction sheet and put this compound here, the actual true reagents you would use is mercury sulfate and sulfuric acid. So you can see where this is a source of water, and your proton source is going to be the mercury sulfate. And so what does C say? Draw the enol that would lead to the product drawn below. So that's what we just did. Okay, this is the enol right here that you would draw that would lead to this product. And is this enol a result of Markovnikov or anti-Markovnikov? Well, the one that they gave is we gave him Markovnikov, and that's what you would get. Okay, if you got this enol, so they're saying, okay, I see what they're saying. They're saying draw the enol. So what's that enol that would lead to that product? Okay, so if you had to work backwards, okay, so this is the hydrogen that came off of the oxygen. So you put that on there, and then you're going to have to make a double bond here. And then that's CH2, CH3, CH2, CH3. Okay, so you see how that's an enol? And this made an aldehyde. So this is the anti-mark. And the reagents you use to make the aldehyde for the anti-mark is the diisolamyl boron, and then the second thing you treat it with is hydrogen peroxide and sodium hydroxide. And that's what they're saying. From the reagent listed at the top, model 3, determine which reagent is necessary to form the regioisomer in number 10C. And this would be your answer for that. Now, I'm going to do a little summary here just for your reaction sheets. So what I would put on my reaction sheets would be the following. So I'd have two reaction sheets. These are two very important reactions. And just go ahead and get the terminal here. And if you do mercury sulfate and sulfuric acid, then the mechanism I expect you to do is straight to the enol. So the mechanism I expect to see when I ask for this mechanism is the enol. And this means your OH, you're going to add water across that triple bond, and you're going to be adding water to these. And so this is the enol, and I expect to see the OH from the water being added to that triple bond. Okay, so and then I expect to see the tautomerization. Okay, and like I said, I don't care whether you do it my way or not, if you want to do the whole full mechanism, but this is how I do it. And you can see that I do the tautomerization here, and I have made a, do you see that that is a ketone? The carbonyl is bonded to two carbons. That's a ketone, and that's considered Mark's addition, and you do that with mercury sulfate. Now, get out another reaction sheet, and what if you add isoamyl boron, and then you treat it with hydrogen peroxide and sodium hydroxide? Then what enol do you get? You get this enol. Okay, so now you have water added, and the OH is added to the less substituted. And this is the anti-mark. And so then when you do your tautomerization, you get and this is an aldehyde. Do you see that your carbonyl carbon is bonded to a carbon, but also bonded to a hydrogen? That's an aldehyde. And so terminal alkynes can give you, with the diisoamyl boron reagent, it gives you aldehydes. With the mercury sulfate and sulfuric acid, you get the ketone. Now that's only with terminal alkynes. If you got an internal alkyne, then both of them are equally substituted, and so you would get both of these, you would get ketones. So you would get either one of these reagents would give you a ketone. Because you would be adding the, you're basically adding water across the double bond, or the triple bond here, okay? And so both reagents would give you a ketone. So the only time you get an aldehyde is with the isoamyl boron, which is a sterically hindered boron that can deliver just one hydride. And that sums up the reactions of alkynes that you are responsible to know. You have additional questions, 11, and you have to put in the reagents for all your different, for 11, and then 12 you need reagents. And that wraps up your POGIL.